This is the 7th video on electromagnetism for A-level physics. The aim of this video is to understand how Faraday's law applies to a loop and a bar magnet. So to start, we're going to need a picture of a loop and a bar magnet. Here we have a magnet with a magnetic field coming out of the North Pole. The magnetic field hasn't been drawn on the South. It's not necessary, it's not going to feature in this problem. On the right we've got the coil. It's got many turns. If we recall Faraday's law, it tells us that if the flux or flux linkage through a loop or coil changes, an EMF, so voltage, will be induced. It also tells us about the rate at which this will take place, but most importantly it tells us that if we change the flux through a loop, we'll end up inducing a voltage or an EMF in that loop. One way we could do that is by moving this magnet to the right. If we do that, more of its field lines will go through the coil. So we'll pick the magnet up and see how that works out. So take the magnet, drag it to the right some distance. Okay, we'll park it about there. So you can see now, instead of just having the red line go through the coil, we've got the blue lines coming in as well. So if we've got more field lines passing through a surface, we've got more flux, and because we've got multiple turns here, we can say we've got more flux linkage. So flux linkage has changed, so we'd have to end up inducing, we would end up inducing a voltage inside this coil. So we could place a voltmeter here across the coil and it would pick up some reading. Now it will only display some EMF, it will only show us an EMF as being produced as long as that magnet keeps moving. Because the moment it stops moving, even though the flux is higher, the flux is no longer changing. It's all about changing the flux. So it's a very short-lived effect. We could go further with this. Just drop that right there. We can now choose to take the magnet forwards again. Let's say that we take the magnet forwards and we go further with it this time. Let's get all the way to that sort of level. At this stage, we can see that the yellow, the green, the blue and the red field lines, and even on the lower side, some of the white field lines have gone through the loop. We've increased the flux massively. If we change the flux by a lot in a small amount of time, so if we were to move that magnet really close like it is now, in a short period of time, we will have changed the flux linkage through the loop at a high rate. Rate of change of flux linkage determines the EMF. So in that case, we will have generated a larger EMF. We'll just pull that magnet back into its starting position. We also need to consider what happens when the magnet is moved back away from the coil. So let's put the magnet in position close to the coil. So we've got the green lines, the blue lines and the red line going through. So we've got quite a bit of flux from this magnet passing through the coil. Well, when we drag the magnet backwards, so drag it back through some distance and put it down, we can now see we've only got the red field line passing through this. So we've gone from a high flux to a low flux. It doesn't matter whether we go up or down, we've changed the flux, we've changed the flux linkage through that coil. Therefore an EMF would be registered, the voltmeter would register that. So let's note those ideas we've come up with. The magnet can be moved towards or away from the coil, and in either situation the flux linkage changes. Again, really emphasizing Faraday's law. As a result, a voltage is induced. We also established another point. Faraday's law talks about the rate of change of flux linkage. So if we change the flux linkage rapidly, we get a big EMF. If we change it slowly, we get a small EMF. For the magnet coil situation, that translates to this. If the coil and magnet approach rapidly, a large EMF is induced. And the flip side of this is if they approach each other slowly, then a small EMF is induced. And then we can run all of this in reverse. We can go the other way. So if we pull them apart rapidly, we get a large EMF. If we pull them apart slowly, we get a small EMF. If we wanted to make this system that we've set up here, so this system with the bar magnet and the coil, more useful, we'd need to keep moving the bar magnet and the coil together and away from each other over and over again, lots of times, ideally rapidly, to generate a significant voltage. If we do that, we can generate voltage on a cyclic basis. In practice, it's not ideal to move two things back and forth, and we'll see in another video that it's actually really quite good to rotate a coil inside a magnetic field, but we won't deal with that right now. One last thing we need to look at is rotating the magnet. Not a proper rotating loop system that we would really use to generate electricity, but just what happens if we rotate the magnet. So we need to draw out what we're dealing with here. So here we have the magnet drawn in the starting position, so we'll call that position 1, and then we rotate it around that green point, or the axis that runs through that green point. So we turn this so that the north end is directed up, and we end up with a situation that looks like this. We used to have a lot of flux going through the coil, right? We can circle all of those lines and say they were passing through this coil. So a substantial flux linkage. So we start with a high flux linkage. We've then rotated to position 2 here, and we now have no flux linkage. None of those field lines that we used to have coming through the coil go through the coil anymore. No field lines going through, no flux going through. So we've had a change in flux. Going from 1 to 2, the flux decreased. But Faraday's law doesn't care so much about increase or decrease. Faraday's law relates strictly to changes. Well, a decrease is a change in flux linkage. So we will induce an EMF. So we could have put a voltmeter across this, and while we rotated it, only while we're rotating it, not once the magnet stopped moving, not once it's stopped in this position right here, but while it's moving, we will induce an EMF in the coil. We will be generating electricity. Again, if we rotated it back into this position here, we'd go from a low flux, no flux, to a high flux. That's again a change, so we would induce an EMF. And then there's one last point. If the coil is rotated rapidly, the EMF will be large. And the opposite of this is true. If the coil is rotated slowly, the EMF induced will be small, because the rate of change of flux is small. Again, we're going back to Faraday's law, thinking about the rate of change of flux and how it dictates the size of the EMF. Okay, that's all.